I want to welcome you to this public lecture by Karl Haber. My name is Beate Heinemann. I'm a professor here in the physics department and a scientist at LBNL. And I'm also the director of a new center, which we're founding just now, which is the Berkeley Experimental Particle Physics Center. And that's actually that's the center that's hosting this public lecture by Karl. So just wanted to tell you briefly about the goals of the center, because it's also related to this lecture. So the goals of this center is to foster collaboration between various areas related to particle physics, to better address the problems that nature poses to us, or to figure out what nature is all about. So for instance, there's various ways to look for dark matter in the universe, which we know there's a factor 6 more dark matter in the universe than there is real matter, the matter as we know it. And members of the center are playing a really leading role in these, in understanding what dark matter is. And one of the major focuses of the center is really to try to ensure that we can make the technical innovations that are needed to address the problems that we're facing in physics today. So historically, it's been really technical innovations, partially undirected even, that have made major breakthroughs. Very famous is, for instance, the development or the innovation of the cyclotron by Ernest Lawrence here in Berkeley, which ultimately led to all accelerators in the world, and ultimately, for instance, led to the discovery of the Higgs boson in 2012. And obviously, he didn't have that in mind. He just innovated at the technical level, and so that's key to making progress. Anyway, so in that spirit, we have now a workshop here which is called Connecting the Dots, which is actually on the computational challenge of recognizing patterns in particle physics experiments. This is a big challenge at the Large Hadron Collider experiments. And related to that is actually the research and also this lecture of Karl Haber. So Karl Haber is an experimental physicist. He received his PhD from Columbia University, and he's now a senior scientist at Lawrence Berkeley lab here. His career has focused on the development of instrumentation and methods for particle physics experiments, for instance, at the Fermilab Tevatron Accelerator near Chicago, and then also at the Large Hadron Collider at CERN near Geneva. Since 2002, he and his colleagues have been involved in aspects of preservation science, applying methods of precision optical metrology and data analysis to early recordings, and this is what he's telling us about today. And for this work that he's done, he's been awarded the 2013 MacArthur Fellowship, a very prestigious fellowship, and he's also a fellow of the American Physical Society and the John Simon Guggenheim Memorial Fellow. Okay, so I'm very pleased to introduce Karl now, talking about seeing voices.
Thank you very much. I'm really happy to be here this afternoon and to be able to give this first public lecture for the Berkeley Experimental Particle Physics Center. So as Beate said, the talk's going to be about sound recordings. I called it Seeing Voices, which is supposed to already be a bit confusing. So basically, I'm going to tell you kind of 3 interlinking stories today. And the theme is finding ways to preserve and create access to very early sound recordings. And so one aspect of it that I hope you'll take away is that there are really meaningful ways that we can apply quantitative methods to problems in the humanities. And another is that our history, as represented in recorded sound, has a number of important challenges if we want to preserve and create access to that history. And then finally, that early sound recordings give us a really interesting window on the 19th century, the late 19th century, which was kind of the heroic period of invention, where really, if you think about it, the analog and digital concepts that pretty much completely underlie this information world that we live in now were really first explored. And the images here are supposed to kind of evoke these three themes. Here's some journals that represent scholarly work on science in the service of preservation. Here are some historical images that kind of relate to how recorded sound represents our history and our culture. And then some of the kind of key figures in invention. You'll recognize, obviously, Thomas Edison. So what's the relationship? So the topic that I'm going to talk about today has its origin actually in pattern recognition, which is the analysis of images to extract kind of meaningful information. And so this is a picture of a group of people, obviously from a long time ago, but some computer code has been run on this image and it's found all the faces. If you have a digital camera, you're familiar with that process happening all the time. Here's obviously some biometric data that's in front of this woman's face, and it's used to find features automatically that can be used for identification purposes. So pattern recognition is a very important subject, and it's ubiquitous. It occurs all over the place. And in fact, as Beata said, it's the subject of the conference that is being held now here at the university called Connecting the Dots, using new ideas about how pattern recognition can be used in the physical sciences. So what's the connection to particle physics? Well, particle physics, it turns out, relies very, very heavily on the use of images as a primary source of information about the subatomic world that we're trying to study. And this characteristic of particle physics really can be traced to the very origins over 100 years ago of particle physics as a field, and it remains a very important aspect of particle physics today. Obviously, we're still having this conference. Particle physics shares the use of images with other fields like astronomy and, say, cell biology, but certainly not with all the sciences. Not all the sciences use images in such a primary way, but particle physics does. So here's some examples. Okay? This are three pictures that are really kind of, tell us some things about the physical world. This one is just telling us that this pin is radioactive. Okay? And the reason we know this is that this vessel is filled with a vapor, and when the alpha particles emanate from the pin, it causes condensation, and we see the tracks of droplets. It's called a cloud chamber. This is a picture taken in a cloud chamber a long time ago, but it's a really important picture because it actually established that there's such a thing as antimatter. So here's a very fundamental picture in the history of science. Here's another really important picture. This picture, again, kind of a confusing, messy-looking image, but it actually established that the electromagnetic and weak forces are unified. So pictures are very, very fundamental to the way particle physicists think about the world. And today, we work at large facilities. This is the Large Hadron Collider at CERN, where many of us do our research. It's a ring of magnets deep under the terrain of France and Switzerland near Geneva, which obviously has been featured in the news prominently with the discovery of the Higgs particle. Key to doing physics at a facility like this are these very, very large pieces of equipment that effectively are, you can call them cameras. They collect images of the physical phenomena that we're trying to study. And if we're lucky, what we discover can actually be described on a T-shirt. So again, imagery is a very important aspect of physics today. Of course, the images are a lot more complicated than those really fundamental ones that I showed you a moment ago. So this is data, which is an event that was part of the discovery of the Higgs particle. But and it's the topic of the conference is actually, how do we get information out of images like this, which have so many features and so much structure. So I hope I've convinced you that as a physicist, I care about images and that images contain a lot of interesting information. So now what's the connection to sound? Okay, well, I was riding in a car, and I was stuck in the traffic on the Highway 880, going back and forth between Berkeley and Silicon Valley when we were building Atlas, and I heard a report on KQED, which was an interview or a speech by this man. His name is Mickey Hart. He's a famous Bay Area musical figure, a percussionist. Many people will be familiar with him. But in addition to his long career in music, he's a passionate advocate for the preservation of the world's recorded sound heritage. Okay? And he's written this book called Songcatchers, which talks about all the people that went around over 100 years ago recording people's music, their cultures, their stories, their songs, and trying to preserve cultures that were perhaps threatened. And what he said in this radio piece that I was listening to is that sound recordings are of great historical value. He said that there were a lot of them, for example, millions at the Library of Congress, and that sometimes the older ones in particular can be damaged, they can be delicate, or in some ways endangered. And so these pictures here are supposed to kind of suggest or evoke this issue. You can see things that obviously are cracked or falling apart that just by their appearance, I think, strike you as artifacts or old objects. And they're in a wide variety of formats. There are some that are shaped like discs, some that are shaped like cylinders, some that are on sheets of plastic. And that pretty much we don't maintain the technology to play these things back. So I really was not familiar with this issue at all, but listening to it and being a person who cares about pictures, I asked myself the question, could we turn a sound recording into a picture? Because if we could turn it into a picture, then we could use some of the same methodologies that we're used to using in particle physics to understand data in this very image-based way, and maybe extract enough information from the pictures to enable us to play these recordings in a very non-invasive way, a way that would preserve the fundamental material. And it's interesting, I kept thinking about there was a comment made during the conference where somebody said, somebody asked the speaker about data, and he said, well, whatever data you give me, I'm going to make it into a picture, or I'm going to make it into an image. And that's, very much, a kind of mindset that we have in particle physics. Let's, think about it as a picture. So, much more. So, okay. So for that to be, more specific, I need to tell you a little bit about what sound recordings really are, because most people think that sound recordings are the things that come out of their iPhones or their MP3 players. But they're actually much more than that. So what is a sound recording anyway? Okay? So you know what sound fundamentally is, and you pretty much know either explicitly or intuitively that sound can be transferred from one material to another. And I mean, the easiest way to see that for a child is to feel the bottom of a paper cup and feel the bottom of the cup vibrating when you speak into the cup. So now, how was sound recorded? Well, sound was first directly recorded by people who realized that they could capture this fundamentally mechanical effect permanently into a soft material through deforming it or engraving it in some way. That was the insight that you've effectively, we associate with, say, Thomas Edison or somebody of that ilk, realizing that you could actually permanently capture that action in a soft material. And Edison realized that you could reproduce sound by basically reversing the process, taking the process used to capture the sound and using it to drive the same mechanism backwards. So it seems obvious now, but it was obviously a huge thing at the time. And the pictures that are shown here are supposed to evoke this. So this is actually a piece of tinfoil, which was upon which sound was recorded in 1878. And if you zoom in on this piece of tinfoil, you can see this sort of repetitive pattern. That's actually the impression of sound that's been deformed into the surface of the foil. So this is pretty much the invention of sound recording and reproduction, which occurred just a few months before this particular foil was recorded. Turns out, and I'll come back to this later, there was a man who recorded sound almost 20 years before this by basically inscribing the sound on paper. So he had a recording system, but he couldn't play it back. Okay? He couldn't reverse the process since it was just a drawing. Later on, it was realized that tinfoil, obviously not a good material, so they moved to cylindrical. This was meant to be wrapped around as a cylinder. They moved to cylinders that were made of wax. And here's a kind of a micro photograph of the structure of the surface of the wax that, again, has had sound embossed into the surface. And then here's the more familiar disc format that some of you may remember. Again, there's a surface that's been modified, and the sound is represented in changes in the shape of the surface. So I've sort of answered the question, could I turn sound recording into a picture? Because obviously here are pictures of sound recordings. But more specifically, this thinking along these lines grew into a project which we call the Berkeley Optical Restoration Project. And again, we asked the question in a more technical way, could we use optics to digitize a recording and create a picture, right, without making any contact to the material, and have that picture be so detailed, be sufficiently detailed, that we could then write a computer program that would process the image, that would do pattern recognition on the image, identify the structures of the image which contain the sound, and then recover it. And if you could do that, you could come back to Mickey Hart's list of issues and pretty much address them. You could restore, stabilize delicate or damaged media because there's no contact. You could essentially turn this into a kind of almost like an automated process to handle a lot of recordings. You could do a lot of work to just assess the condition of materials through these very high resolution images and escape the need to have these kind of legacy playback systems for all these different materials. So up at the lab, we started to talk about this. It was almost like a joke for a few years in the early 2000s. But eventually, some experiments were done on like Saturdays, and it was shown that it could actually work. So we ended up writing this paper, Reconstruction of Mechanically Recorded Sound by Image Processing, of Vitaly Fadeev, was a postdoc at the lab, and we worked on this together. And we took that paper, we sent it to just a couple people that we found on the internet at the Library of Congress. And the library, which is a very, very forward-looking institution that really thinks about its role as the nation's library and dealing with issues that across the spectrum that face materials that contain information, they responded to us with a lot of interest. And this really led to a collaboration which continues to this day with the Library of Congress and really enabled this whole thing to develop. Okay, so let me tell you a little more about the characteristic of sound recording so that you'll understand the methods that we use to actually create the images and then how we analyze them. Okay, now there are many different types of recordings and all different formats and things that people try to, obviously don't have the time to list every one of them, and you probably wouldn't want me to anyway. But so I want to kind of break it into some just simple categories, right? So the two basic formats, like the Mac and the PC, if you like, of sound recordings, were the cylinder and the disc. Okay, you never see the cylinder anymore, but the disc obviously has continued in modern forms. Cylinders were typically used from the late 19th century until, say, around 1930, something like that. And the sound was impressed into the surface by a vertical groove, a groove that went up and down. Okay, so you've got to keep that in mind, the vertical recording. And these recordings were essentially all done acoustically. There were no amplifiers. It was all done with mechanical linkages and so forth. And they could only record up to a few thousand hertz in frequency. Okay? And the amount of movement in the groove was actually very small. Okay? So they had a very small modulation, shallow groove, not a lot of bandwidth. But they were the only game in town for a while, and so they had a very important role to play. Later, the disc had a deeper groove, which typically moved from side to side. So most discs have a groove and it moves further, so they had a bigger range, louder. In the 1920s, people introduced amplifiers and electrical systems, so you had electrical recordings. So mostly when we talk about discs, we talk about grooves that go from side to side, laterally, and we talk about cylinders, they go up and down. And then, of course, the kind of materials that you find on recordings fall into sort of, you know, two big categories, unique or commercial. Commercial means things that were stamped or molded or produced for mass consumption. There were cylinders that were made of plastic that were available kind of in this time frame, and discs, which obviously continued into the vinyl age, and you can even buy disc records at Target today. But mostly, you know, they were popular in the 20th century and, you know, into the late years of the 20th century. The unique recordings were either early experiments before 1900, what are called field recordings, meaning unique recordings that were made out in the field, say of Native Americans or Pacific Islanders or people in a village in the Ukraine. And then transcriptions, these were studio takes, one-of-a-kind radio broadcasts, and they were created in these periods. So you'll find these types of recordings, both in format and in content, appearing later in the talk and you know, throughout this history. So what does sound recordings really look like in terms of a measurement problem? Because obviously, we're physicists, we need to measure. So here's that 1878 tinfoil. And it was wrapped around a cylinder, and so the groove would go like a helix, right? Around and around and around. So I've drawn these little red lines, and this shows what the surface of the foil looks like, both across the groove and along the groove. So along the groove, you might not be surprised, it's going up and down. Like sound, it's a wave that goes like this, up and down. Essentially, the height tells you something about how loud it is, and the period tells you something about the tone. So if it was an octave higher, you'd see twice as many wiggles in the same time. Okay? How much does it wiggle? It wiggles by about, in this case, about 50 microns. So 50 microns, according to Wikipedia, is the average thickness of a human hair. Okay? So that's the scale, right? Now this is actually a pretty loud part. There are much, much quieter things, and the noise level, you know, the baseline is submicron. So this is a really old technology, but it's using very, very small physical quantities to record physical effects. If we look across the groove, we see the shape in this direction, and typically these are separated by about 1 millimeter, so that was the pitch of the groove as it goes around and around. And again, this was a vertical recording, just like a cylinder, because you can see the surfaces going up and down. If we fast forward to the 1930s, and here's the disc now, which is, you know, selling like hotcakes commercially, the groove is moving from side to side. So the grooves all have the same depth, but they move this way. And they move a typical thing of from a fraction of a micron to maybe 100 or 200 microns. So bigger movements, but side to side. So, but not hugely different. So it's pretty interesting. I mean, Thomas Edison introduces this technology, and he basically got the numbers right, and people have basically stuck with those numbers ever since. Now, if we're going to take pictures of sound recordings and actually get reasonable information from them, we're going to need to measure from the submicron level to these larger amounts, and we're going to need to measure this whole thing. So the interesting thing is we need to measure submicron structures. If you actually unwind one of these things, it would be like 150 meters long, you know, the groove itself. So we're doing really tiny measurements on really, really large things. So it's big data, if you like. Okay, so the process that we kind of conceived of to take this data and then do pattern recognition on it was to build some sort of a scanning machine, still to be defined in this talk, and with this scanning machine, create very, very detailed profiles of the surface. In this case, it's a cylinder. In another case, it might have been a disk. And then combine those profiles into in this case, a topography, a three-dimensional map of the surface where I know the depth at every point on the surface with sufficient precision to capture the nuance of the sound at its lowest level and its largest. Once I have that map, it's a big chunk of data, I can archive it, and that can become an artifact of this measurement process. But then I can pass it through an algorithm that can actually calculate how would the needle move through this surface, and what would be the sound that would come out if the needle moved in that way. And then I can format that as a digital audio file, and we can listen to it. Okay, and we will in just a few moments. So that's the basic idea. But to really make this work, we had to identify the right things to go inside this box. Okay. So I told you that on disks, the groove moved from side to side. It was a lateral groove. So one technique that we could use to get information from this kind of a groove is photography. Okay? But it has to be the right kind of photography. So we built a microscope which had a digital camera on it. And this microscope had the right magnification to map about a square micron on the surface to about a pixel in the imager. And we trained the light on it so that all the light was perpendicular to the surface. Okay? Once you get all the light going perpendicular to the surface, you get a very, very interesting image. You get a very high contrast image of the surface because only flat things reflect light back up, and everything else sends the light off in some other direction and it never gets back into the camera. So we were able to turn these sound recordings into these really striking images where you can really resolve the structure of the groove, and you can really see where it's moving. Interesting features that come out when you do that is scratches look dark because they scatter the light in all different directions. Dust particles look dark because they scatter the light. And the walls of the groove, they look dark because they're going to send the light off in some other direction. So right away, you get access to the fundamental structures in the material that carry the information. And when you have a picture that's got this much contrast in it, there's a technique which is called edge detection, which enables you to very, very rapidly locate all the places where the image goes essentially from dark to light quickly. Okay? So edge detection is used all over the place. It's actually a very simple transformation that you can apply to an image very efficiently, very quickly. You can take an image like this, which might be in its full-blown representation of the entire surface, many gigabytes of image data, and suddenly you can reduce it down to just the interesting aspects of it, which are now a much, much smaller set of information. Okay? There are cameras that can perform the necessary imaging that essentially run a few times slower than the real time represented by the content. So if the record was 5 minutes long, maybe it takes 15 minutes to measure all the edges, all the pixels, and then convert them into edges. So it can be a pretty efficient process. Interestingly, to get this kind of resolution, you need cameras with really, really narrow depth of focus. And in this case, you have to have a very active control of focus. And, but you can do that, and you can get this kind of very striking information taken right out of the images. Okay? Now I told you that the cylinders actually have grooves that are vertical, that go up and down. So photography is not a good way to get information from the third dimension, right? I can take a picture of this room and I can sort of estimate, because I know kind of how big a person is, the distances, but it's not precise. So to get the third dimension, you need to do something else. Maybe it's interferometry or range finding or structured light. There's a whole bunch of ways to do it. The technique that we learned about that turned out to be the most effective is a form of confocal microscopy. So we're in the biology department here, and there are probably a lot of confocal microscopes in this building. But the type of confocal microscope that we used is called a color-coded or chromatic confocal microscope. And it works differently than many of the laser-based confocal microscopes that biologists might be familiar with. So the way it works is it takes white light and it puts it through a lens and focuses it. But that lens has an exaggerated chromatic aberration. So it takes the different colors of light into different focus points. So now you can correlate depth with color. Okay? So this device, which is represented a little more completely here, takes white light, puts it through a pinhole. This is a lens. You get this loci of foci. And then as you pass a surface through that, only certain colors reflect back up into this conjugate point, and can be analyzed by a spectrometer and can tell you the depth. It's a commercial device. And it's got a lot of uses in dental work, in quality assurance, in optics inspection, in art preservation. It's used widely in, there are, of course, biological applications to confocal microscopy as well. But the amazing thing about this device is that it has a startlingly good resolution in this direction. In the case of the one we used, sort of 50 to 100 nanometers per point. And it comes in a package where you actually have 180 of these running in parallel. So you can sweep them across surfaces and you can create these topographies. And in fact, the pictures I showed you of the surface of the foil were actually collected with this confocal microscope, made by a very innovative company in France, which is called Still. And we've used these things very productively now for many years. So it's this tool that we found is effective for three-dimensional measuring. It's the microphotographic approach that we found is useful for two-dimensional imaging. Okay? So we put all of this together into a machine, and that machine has the confocal probe, the microphotographic cameras, systems for controlling the position, rotating, spinning, and so forth, so that we can systematically create these large data sets that we need of the surfaces of these sound recordings. We call the machine IRENE. It's because the first recording that we looked at, that we described to the Library of Congress, was a recording of Good Night, Irene. Some of you may know that song. A lot of children like it because they think it's a lullaby, but it's actually about murder, adultery, suicide, and drugs. But for us, it's also a good acronym. It's image, reconstruct, erase noise, I'll tell you why, and then etc. So that's what we call it. Okay, so there are actually 5 of these machines now, one in Berkeley and others in other places, and I'll tell you about that in a moment. So how does it really work? I mean, how do we really deal with the data that comes out of things, out of such a measurement? So I'll give you an example in the case of the disk. So we spin the disk is warped, it's not flat. So we need to keep it in focus at all times. So we have a laser that actually measures the warpage of the disk, and it controls the camera so that it's always a fixed distance. Okay? The camera is actually a line scan camera, so it just takes one line of pixels as the disk rotates. So what that does is it takes this circle and it unwraps it into a huge rectangle. Okay? So here's a little chunk of that rectangle. And then that rectangle is sliced up into pixels because it's a digital image. The pixelation is our time sampling. Okay? And it turns out that you very naturally get time samplings in excess of 100 kilohertz by this kind of a measurement. So you can sample way beyond the range of the material that's actually been recorded. Then you do edge detection on these images, and you find the contours. Now, the contours are really powerful because they tell you something about a very, very regular structure, a groove that has a certain geometry and it just moves around. So once you find things that don't match the geometry of the groove, these little dots or this little disturbance, you know that's damage. That's going to create noise in the recording, but you find it immediately in the image because it doesn't look right. Okay? So there's a pattern recognition handle on noise reduction that pops right out of the fundamental nature of sound recordings. And you measure that distance for every time slice, and it has a very nice little histogram with tails. If a point on the recording is in the tail, it's bad. It's not something that's going to contribute noise. So you can actually drop those points from the data set and just smoothly join the data on either side, if you want to. So you end up with a contour of the groove. Now, that contour tells you how the needle would have moved if you had actually played the disc. But you have to now understand how the needle itself actually works. The needle works by a coil that moves in the field of a magnet. So it's induction. Therefore, the needle is actually turning the information of the needle's, sorry, the needle is turning velocity into sound, okay? So it's not the shape of the groove, it's the speed of the needle. That's the sound. So we have to take all the data that we measure and massively differentiate it numerically to turn it from position into instantaneous velocity. So that's another kind of processing that you have to do. But once you do that, you end up with something that is kind of trivially transformed through just simple arithmetic into an audio file that you can then play. Okay, there are many technical issues that come up. You know, you have to obviously deal with all the measurement issues of focus and stability and triggering and so forth, and then all the issues of analysis, extracting the data, actually tracking the groove, modeling that needle, and so forth, but that all kind of got worked through. This, just to illustrate kind of, you know, where it can become a problem, here's obviously a disk broken into many pieces. So the images of that disk have all these sharp discontinuities in them because everything starts shifting around when it's broken. But you can actually use pattern recognition and other tools to find all the linkages to actually tell you how a needle would have moved through a disk if it hadn't been broken, and therefore you can play it. So there's a very powerful suite of software that ended up being built up by people at the lab, by students over the years. And this is just kind of an example of one of the software packages that, in this case, deals with data that comes off wax cylinders. So this is an image of a wax cylinder. Think of the cylinder as a tube. I slice it and open it up. So when I open up a tube, it becomes a rectangle. So think of this as an opened tube. And it was data that was taken with the confocal microscope, so it's a depth image. So we code dark as deep, light as shallow. So what you're seeing here are the grooves, and the needle would have done this. It would have come down and jump, come down and jump, and so forth. If we zoom in on it, you can see very nicely the structure of the surface. So it's down, up, and so forth. Now what about all this kind of random looking stuff? Well, that's actually a mold that eats wax, and it's one of the real problems with recorded sound collections is that there are many processes that lead to their degradation. One of them is just this hungry mold that actually eats the information. However, you can notice right away that this stuff doesn't look anything like the very regular structure of the groove. And I don't know if you can see, but see all the orange highlights? That's actually pattern recognition code finding all this stuff that doesn't look right and saying, does this really belong in the image? Do you want to delete it from the image, like in the Photoshop sense, and actually smooth across? And you can do that if you want to, and you know, that's activated by various controls. Okay, so to take another step, all of this is actually embedded in a whole system of user interfaces, analysis systems that watch the data acquisition, process things, and so it can actually be used in an archive. In fact, all of this stuff, which I won't tell you all the detail, it's a full production level system that was built up for the Library of Congress to their specification, and it allows them to efficiently transfer disks one after another, and take the data that's necessary to take. Okay, so a lot of talking. Does it even work, right? So I'm going to show you now some examples and take you through the rest of the talk. Really, we're going to listen and compare various recordings and try to understand some of the performance issues and some of the history. Okay, so first of all, so sound has amplitude and frequency. So one of the things that we wanted to do is we wanted to know that if you just had a simple tone on a record, could you reconstruct it with the right frequency and the right amplitude? So I don't know if you guys have ever been down on Parker and 10th, but that's Fantasy, the old Fantasy Studios building. So there's a man there who's a very experienced recording engineer, and he actually had a machine that could cut records. And he kind of befriended us, and he cut records for us that we could use for test purposes. So he cut us this record that just had sine waves in it. And he cut all different sine waves at different frequencies, and we scanned them and with IRENE, and so what do they sound like? Well, just like that, okay? Not too interesting, but at every frequency that he cut, we were able to reconstruct that frequency and that amplitude. So that basically shows, in some sense of calibration, that you can, what you put in comes out. He also cut something which had a lot of audio richness to it, and we played that as well, and it sounds like this. Okay, so I think this is supposed to indicate that at some level this thing is behaving like a record player. I don't know if you guys recognize that music, but it's by a band from El Cerrito. Some of you may know who they are. Now, okay, that's all and well, but what about material that's not in pristine condition, that was not cut specially for us? So as a kind of counterexample, this is a wax cylinder that was actually cracked, and it was from 1906, and it was part of a mechanism in this fortune-telling machine. It's like in the movie Big, you know, you put money in, and instead of whatever the big thing did, it actually would tell you your fortune. So this came from the Montana State Historical Commission. They brought it here to Berkeley in 2010, I think. So this is what it sounded like when you actually scanned it and played it.
You will soon go to a ball or large gathering and meet a new friend. A sincere friend seeks to help you in matters of importance to you. Your troubles can be avoided by changing your attitude towards them. You will have unexpected good fortune in a letter. The first years of your life will be the unhappiest. You will be married 3 times, each time more happily. A person who has made trouble for you in the past will become your friend.
Did you get that? Yeah? Well, it's pretty impressive because like that, all that stuff still applies, right? Like you will soon go to a ball or lodge gathering and meet a new friend. That could be today, right? Okay. And also, I mean, all this stuff applies to rock musicians from the 60s and the 70s too, right? So I think that, you know, kind of gives you the sense that also it can work in this completely different domain on material that would essentially be otherwise unplayable. Okay, but really, is this a good technique? Is it better or worse than playing things by standard methods? Well, I showed you that piece of equipment, and you could guess that it's not inexpensive, right? There's a lot of scientific grade hardware, and so you're going to have to make an investment if you want that kind of technology. So there's no simple answer to this question, is it better or worse? So this optical approach, it essentially renders, and I'll show you that, a whole range of otherwise unplayable materials playable. So that cylinder of the fortune-telling machine, it wasn't going to get played. Okay, it's not playable. And I can show you, and the same thing with the tinfoil, that was not going to get played. So, you know, delicate and damaged materials essentially are now playable through this imaging. There are other archaic materials that might be playable, they're more on the edge, but this approach really ends up working very well on those materials, and in many cases gives you improvements over a normal playback method. On the other hand, for commercial recordings, which people refer to them as shellac discs from the 30s, 40s, and so forth, those that are in really good condition, the traditional methods, which are much quicker and less expensive, those are preferable, I would say. But once the material crosses a certain line and it's degraded, it's noisy, it's of questionable to play it, this technique really brings in, I think, a lot of power and a lot of capability that people didn't have before. The other thing which emerged as we learned more and more about this is that these optical methods can actually capture much higher frequencies than a stylus can capture. In many cases that doesn't matter, but in other cases it really does. So let's look at a really interesting example of that. Okay? So here's the wax cylinder again, and you remember I told you that on a wax cylinder the sound is recorded in a vertical groove. Okay? When you want to play one of these things by the normal method, you take a stylus and the stylus nestles down in the groove. Now the size of that stylus is set by the size of the groove across. So there's a certain scale that you are forced to use based on the geometry of the material. Now, as the surface starts to undulate faster and faster, meaning the frequencies get higher and higher, At some point, the stylus is too big, and it can't actually measure properly the surface anymore. That's called a tracing or scanning loss in the old audio terminology. The interesting thing is that the optical probe, the point of light from the confocal microscope, is insignificantly small on a scale set by the stylus. And here's a picture of the frequencies in a sound recording as measured when they played it with a stylus. And you can see above about 2,000 or 3,000 hertz, the power that is being measured by the stylus just drops dramatically. Okay? Whereas when you measure it with its optical probe, since it's so small, it's essentially flat turns out to about 100,000 cycles per second. So you can capture much, much higher frequencies. Now, why do I want to capture high frequencies? It doesn't seem like there's actually much out here anymore. Well, there's a good reason. The reason is that even though the recordings contain audio, deliberate audio that dies off after a few thousand cycles, the noise due to damage, scratches, cracks, mold damage, has high frequency content wherever it starts and ends. And having access to that high frequency information allows you to do a much more effective job in doing the pattern recognition and identifying the noise features and removing them. So it's a very powerful handle that you get when you have this kind of detail available to you. Let me just play you, this is not a demonstration of the noise aspect, but just the difference in the frequency response for the same recording. First, we're going to hear how it sounded when it was played with a needle. Okay, and here's when it was played with the optical probe. Okay, and that should be clear also. This is a couple tens of milliseconds of audio, but you can see it's the same bit of the audio as measured optically and on the stylus, and you can see all the high frequency information that's actually being picked up and not picked up in the other case. Now, what about the noise? So here's a piece of a wax cylinder that actually is showing all this mold damage. This particular image comes from a cylinder that actually is an asset of the University of California at Berkeley. It's in the collection of the Phoebe Hearst Museum of Anthropology. It's a recording of Ishi, who was recorded in 1911 by Professor Kroeber and Professor Waterman. It's a story of, most of you are probably familiar with the story of Ishi. And in this particular recording, I'm going to play you the stylus version, and you're going to hear what the mold damage does. And then I'm going to play you the optical version that takes advantage of being able to use pattern recognition to find all of this stuff and actually subtract it. So here's the stylus version of Ishi. Okay, and then the optical version. So that crunching sound was what was happening when the stylus was passing through the mold damage region. So that noise reduction is not something that you could have done otherwise, but having this additional high frequency information allows you to do that. Okay? Obviously, this is an easy one. Broken discs, they're just by definition not playable, but you can scan them and you can do image processing to reassemble the broken pieces and obviously play them. So
here's a silly ditty, you can sing it right away. Now here is what you say, so sing it while you may. Here's a silly jingle, you can sing it night or noon. Here's the words, that's all you need, cause I just sang the tune. Oh, I don't wanna, you can have it.
Okay, the next line was sort of offensive, so okay. All right, look, the partnership that got started when Vitaly and I sent that paper over is really, it's ongoing. And it's really grown into a lot of really productive collaborations with many other institutions. And really the library has kind of told us kind of where to go with all of this. And so over the years, I mean, this has been going on for about 12 years, you know, faster and more robust hardware and software got developed. Recently, about a year ago, one of these IRENE systems was put in the Northeast Document Conservation Center, which is an organization near Boston, and they actually offer this technology as a service to customers. So for example, the Harvard Library Poetry Collection recently had some discs of Ezra Pound, T.S. Eliot, and Wallace Stevens that were scratched through, played with that system. The other thing, and it's what I want to focus on now in the remaining time, is we've gotten the opportunity, once it became known that this technology existed, to really play examples of the key historic milestones in the development of sound recording. And I want to share those with you now. Okay, that's the system at the Northeast Document Conservation Center. I also want to mention that we have two of these systems at the Library of Congress, and we have a system at the R.J. Muthiah Research Library, which is in Chennai, India. So those are the 5 systems that exist today. Okay, so the first, you know, historical recording that I want to play for you was created in 1887. It belongs to the Edison National Historic Site in West Orange, New Jersey, and it's a talking doll. Okay, and this was an idea that Edison had to market sound recording as a little mechanism that a kid could wind up and the doll would sing. Now, this is actually the first deliberate commercial use of sound recording. It's pretty amazing. And it turns out that it's probably the first known recording of a woman. Okay? So you go directly from this doll to Taylor Swift, right? And you can see the resemblance is amazing, okay? So the whole thing is just a ring. It looks like a gasket or something from a pipe, you know? It's just a ring of metal. It was all bent and deformed. So they brought it to the lab, and it was mounted on a mandrel and scanned with the confocal probe. And it's Twinkle, Twinkle. It sounds really bad. So, but I think you'll recognize it now that I've told you that it's Twinkle, Twinkle. Did you get that? Yeah? Twinkle, twinkle? Yes? No? Okay. This was not a successful product. And Edison called the dolls the little monsters, and he actually had most of them buried. So somewhere in New Jersey, there's a petrified versions of these dolls. Okay. And we found this newspaper article from the time that described them as like Amazon, you know, when they rate the product. You know, this is a complete disaster, terrifying children and costing their parents nearly a month's pay. So it's like the iPhone, iPod, or whatever it is. Okay, so that's the beginning of commercial sound recording and recording of women. Okay. Now, if we go back a little bit later to the early 1880s, Alexander Graham Bell, who had, you know, come off the invention of the telephone, got really interested in sound recording. And beginning in around 1880, he built a laboratory in Washington, D.C. called the Volta Laboratory. And there, for about 5 years, he and a group of collaborators did a huge number of experiments to try and perfect sound recording. And all the artifacts and the notes and the mechanisms and the sound recordings are all in the Smithsonian. So this is an amazing American history collection that has been preserved, at least in its physical form. And a few years ago, the Smithsonian came to us and said, you've got this technology, can we work together to play some of these experimental recordings that had been left untouched since those days. If you're in Washington, if you go to the National Museum of American History, they actually just opened up an exhibit about this collection, and you can hear a whole variety of the recordings, some of which I'll play for you as well. This one is a thin coating of wax, about this big, on cardboard. And it's the only recording that's really been certified and identified as Alexander Graham Bell himself speaking. Thing goes on for over a minute, and it's mostly him reciting numbers and monetary quantities. But at the very end, he identifies that the record has been made by Alexander Graham Bell, et cetera, and I'll play it for you. And the thing that will stand out is when he says, "Hear my voice," and that's actually the name of the exhibit at the Smithsonian, "Hear My Voice." Oops.
This record has been made by Alexander Graham Bell in the presence of Dr. Christopher A. Bell on the 16th of April, 1885, at the Volta Laboratory, 1221 Pacific Avenue, Washington, D.C., in witness Sarah, you are my heart. Alexander Graham Bell.
Did you get that? Yeah. Okay, I went to 1221 Connecticut Avenue. It's actually an empanada stand now. So, okay. Now, this was just one of about 200 experimental recordings that Bell made. And I want to play you one other one because it's remarkable. This is a recording that Bell and his colleagues made on glass using photography. So we've been talking about grooves all this time. This is actually a photographic recording. He covered a glass disc with emulsion, and he built a system where he could bring sunlight in, focus it into this tube, and then vary the light using sound, and write a varying photographic density onto this film. Does that make sense? Okay. The way he modulated the sound, see this thing? It's a tube that's bringing a dark colored dye into a nozzle that's spraying across the light. And he modulates this flow of liquid, and that's how he modulates the sound. So that's pretty Rube Goldberg, but that's what they were doing, okay? Now, here's that disc. It actually begins in begins in the center and spirals outwards. Now you see this big black splotch over here? It's clear that everything stops at this point. They're not recording anymore, and they overexpose, right? We realized that as soon as we saw the disc, but when we actually listen to it, what happens is that at this point in the recording, they're saying, "Mary had a little lamb, its fleece was white as snow," and then suddenly something goes wrong, and they say a really bad word. Okay? So it's pretty amazing because every other recording was very posed. But here you're actually catching these people kind of doing, you know, behaving like they probably normally behave. So we can listen to this. I guess there are no children here, right? Okay. So that's pretty remarkable, right? And then they pick it right up again, and you can hear a big trill. They do lots of trills in old recording. The trill is like brrrr, okay? They were very, very fond of trills, which I think was like a standard sound for them. Okay. Right. So now, a few years earlier, we go to 1878. Edison had just presented sound recordings for the first time with a machine like this, where he had this tinfoil and it was wrapped around a drum, and he, as I said earlier, he embossed sound. So this foil, which is in a museum in upstate New York, came to Berkeley a couple years ago, and it was scanned using the Confocal probe at the lab, and it's over a minute long. I don't have time to play it all for you. It's all online. I'll give you a link that you can listen to it. But it's actually the oldest recording of an American sound. And it's the oldest recording of instrumental music. So you're going to hear a little music. Okay. Now, part of the reason it's so noisy is that it was actually folded 7 times and stuffed in this envelope. And you can see it says June 22nd, 1878. So all the crunching and noise, you know, there's nothing much you can do about it at that point, right? It's been shredded. But I think you could hear the brass instruments playing, right? Yeah. Okay, so now we've got to go to the very beginning and listen to the oldest recording. So the oldest recording of a human voice actually dates from 1860, okay? Way before Edison. A man named Leon Scott de Martinville built this machine that looked a lot like Edison's machine. It had a drum and a horn, but instead of embossing on foil, he actually engraved on paper. So this was a machine that could record sound but couldn't play it back. And these are the paper tracings that he deposited in 1860 in the French Patent Office and the French Academy of Science. So all these other inventions were in America, but this one's actually in France. Sorry. Very interesting is that he recorded 2 tracks simultaneously. One track was the audio. The other track was the direct vibrations of a tuning fork. Okay? Now, why is that a clever thing to do? Because the thing was hand cranked. And so he actually gave posterity a record of the cranking speed of the thing. Now that's pretty good for 1860. Nobody had ever done anything like this before. Of course, Berkeley graduate student would think of that in a second. But you know, in 1860, that was pretty good. Okay. Along the edge, he writes in French, and it's translated, "Au clair de la lune, sung, the pitch is measured by the tuning fork of 500 simple vibrations per second, which writes directly and simultaneously in interlinear space of the song. Leon Scott, 9th of April, 1860. So it's a recording of Au clair de la lune. So this is what Au clair de la lune sounds like in 2008 if, you know, modern American children sing it. Okay. And here's Leon Scott. It's much slower. Did you get that? Okay. All right. So that's, you know, as far as the history goes, that's it. I mean, there's nothing earlier that we know of. So the last topic I want to tell you about, and I think it represents really what the future of this technology is the contribution that we hopefully can make to restoring, preserving, and creating access to field and other direct recordings. So from about 1890, pretty soon after all this experimentation was done, recording is adopted as a tool for ethnographic research. So here's John Harrington. He's recording these people from Panama. Here's Frances Densmore. She's recording in the plains. Melville Jacobs is recording in the Pacific Northwest. Alfred Kroeber and T.T. Waterman are recording in California. They create tens of thousands of unique recordings, which are today on what we would call archaic media, mostly wax cylinders. Here at UC Berkeley, there are 3,000 of those cylinders. And we believe that the main potential for really all this stuff that I've been talking about today, beyond the history, are large transfer projects aimed at moving these large collections into a digital realm with the advantages that this technology could bring. California, these are not the counties. These are different languages that were spoken in California. So California is very rich in linguistic diversity. Here's recordings that were made by Milman Perry. He is a Harvard classicist who in 1930, extensive recordings, 3,000 double-sided aluminum discs. It's an archaic media in South Slavic areas. Interesting, Perry was a graduate of Oakland Tech and UC Berkeley. Then he went to Harvard. His work in Yugoslavia forms the basis of what's called the oral formulaic hypothesis, which is the idea now widely accepted that classical poetry was orally transmitted. And he did that by recording people in the oral tradition in 1930 and showing that the same structural tools and elements are used by these oral speakers in Yugoslavia as you find in the epic poetry. Just as an example, I mean, we heard some recordings from the Hearst collection when we listened to Ishi. This is a recording that Perry collected in Yugoslavia that we scanned on aluminum. And then another prominent example among these direct and unique recordings are lacquer discs, and these are radio transmissions that were recorded during World War II. Oops.
When the lieutenant saw several of his men wounded in fires started by Japanese shells, he dashed from his shelter. Braving the enemy fire, he brought the wounded back to cover, saving the lives of several. A sweeping order from the War Production Board tonight ends the use of iron and steel in more than 400 articles of common civilian use, and thereby puts the finishing touches on the enforced conversion of a great section of our economy. In 90 days, no more fountain pens, pie plates, cigarette lighters, toolboxes, pleasure boats, automobile accessories, streetlight poles, not even bathtubs.
Okay, so I just want to tell you that there's a major new initiative that's been proposed here at Cal, and it's called Linguistic and Ethnographic Sound Recordings from Early 20th Century California, Optical Scanning, Digitization, and Access. And it's a proposal to do a 3-year project here on campus to use this scanning technology to transfer this entire UC collection of 3,000 cylinders. Here's Krober with Ishi. Mary Rose Barrios was a physics major. She graduated a couple years ago, who did an extensive pilot study to support this project. Here's T.T. Waterman. This is one of the Ishi cylinders. You can see University of California, Ishi. This is the Department of Linguistics, the Phoebe Hearst Museum of Anthropology, the UC Libraries, our center, and Berkeley Lab. So hopefully that this will be something that actually lives here on campus over the next few years. Okay, so I'm just going to end with a little parable or thought for you to take with you. So, you know, sound recording in the 19th century, it really utilized technology and methods that I think many people believe could have been applied much earlier. Like there was nothing that Edison and Bell did, even Scott, that, you know, Leonardo da Vinci couldn't have done, right? He didn't need electricity or knowledge of chemistry. So the question is, you know, why don't I have another hour of recordings of Marie Antoinette and George Washington and Benjamin Franklin? So why didn't Da Vinci invent sound recording? So it turns out, this isn't the reason, but I think it's interesting. Da Vinci believed that poetry and music were inferior to sculpture and painting because, and this is what he says, hearing is less noble than sight, in that as it is born, it dies, and its death is as swift as its birth. It's from the treatise on painting. So you see, he didn't even think, you know, he wasn't able to just think, well, I could change that. See? So this is a good thing for students to keep in mind. You know, don't stop at the obvious point, because Da Vinci, maybe he was put on Earth to record sound, but he just never got that. Okay, so this project obviously lives up at Berkeley Lab. Earl Cornell is a very, very prominent player in this thing. He's not here today. We collaborate with the Library of Congress, with the University of Applied Sciences in Fribourg, the Smithsonian Institution, and then these are all the different funding agencies that have, you know, seen fit to support this. And of course, we are very grateful to all those. And something like 40 students have worked on this project over the years, and you can see some of their happy faces. And I think it's great, been a great project for students. They basically come from electrical engineering, mechanical engineering, computer science, physics, anthropology. And I think it's a great opportunity to expose students in the STEM fields to problems in preservation and conservation that have a scientific and engineering basis. So I think it's been a really good educational component here at the university. So I hope I've convinced you that today's digital technology, you know, provides a useful window on this great early period of sound recording, which has such a rich a legacy, commercial, historical, artistic, and so forth. So Bill Viette's the director of the Northeast Document Conservation Center, where this equipment has been set up in Massachusetts, and he says, our ultimate audience is posterity. So that's good. IRENE.lbl.gov is really easy to remember. That's the project website. You can link to all these different things, and you listen to the bad word as many times as you want. The National Recording Preservation Board at the Library of Congress is sort of, that's where you find all the policy ideas behind sound preservation as a national kind of prerogative. So if you're really interested. Anyway, thank you very much. And if you really like those 3D images, Mr. Cohen-Sabin is here today. They're visiting from France, who actually builds those probes. So they're wonderful devices, and I'm sure he'd be happy to tell you about them if you're interested. Questions? Yeah.
Yeah. Are there any? Thanks a lot, Carl, for this wonderful lecture. Are there any questions?
I can't see anything, so.
On these recordings where you had broken records, you could hear the popping when the track crossed the crack. It wasn't very prominent, but you could still hear the popping. Can't you edit out all the pops that relate to the cracks?
Well, okay, so yes, in principle, yes. There's a whole suite of methods for removing pops and clicks in the sound waveforms. We don't typically use them because they're not sort of part of this process, but they're a post-production capability that many audio engineers know how to exploit. We typically deal with them in the image, and a lot of what you've heard, for example, when I played the Too Fat Polka, essentially those discontinuities were mostly gone through the image processing themselves. So yeah, you can. So.
And some of the other early recordings, it's really not possible to remove that overnoise that's still there? Or
okay,
part of it at least? It sounded like the noise was quite different than the recording. The recording had a lot of continuous tones. The noise was all non-harmonic and non-sinusoidal, sort of.
Right. So there are, so the first type of noise that you asked about was very sharp impulse noise. The second type of noise that you're asking about is a more broadband noise. And again, there are powerful signal processing techniques like spectral subtraction that can be used to further clean up sound recordings. And indeed, some of those could be applied to these materials with some liability because they often create digital artifacts and strange things. The purpose of this talk was to focus in on what we can achieve through this kind of measurement process and the image analysis and pattern recognition. For any kind of a real production application, I mean, that would be then the choice of the conservator or the audio engineer. But I didn't feel it would be fair to add other people's noise reduction on top of, I wanted to show like what we could achieve through this process, and then experts, I believe, understand that there's actually more that you can do. But that happens in the waveform domain. We're working mainly in the image domain. Okay, well, you can download that file and you can feed it into your own noise reduction program. Okay, it's all publicly available.
So, how do you? I mean, there was the guy who put the tuning fork there, which is very, very nice. But if you have all these ancient devices, how do you calibrate? I think the audio world. How do you equalize them to so that?
Okay, right. So one question. I think you're asking more than just the speed. Okay, so the first question is, what's the speed? Okay, so lots of field recordings are actually labeled, so you actually know the speed. We have certainly come across experimental recordings, like from Bell and Edison, that in some cases were labeled, but in some cases weren't. In the cases where they're not labeled, it turns out that you can get within about 10% of what was probably the recording speed by a constraint that it needs to sound like a human being. If you differ from what was probably the speed by something like that, it starts to not sound human. So in some sense, it's a cheat because we don't actually have the information, but you have to go somewhere and measure at some point. But definitely understanding speed, figuring out what was going on with speed is an issue, and it's something that we worry about a lot. The other question you asked is more about equalization. So that's a technical term, but it essentially is about what's the frequency response of the system through which the sound passed. So I talked about that a little bit when I told you that in order to go from the image of the groove to the sound, we actually had to differentiate. So the whole process of recording and playing back uses, once they really got going, they very explicitly used frequency-dependent filters as strategies to essentially jam as much information onto the disk as they could fit. Okay? So by attenuating the low frequencies and raising the high frequencies, they reached kind of optimized ways of recording. And a lot of that information is tabulated, and we use it in the models that take the sound through its process. When things were recorded acoustically, there was none of that. Okay? So essentially, you start to look a little bit at the physics of how the diaphragms and linkages had to have worked. And you realize pretty quickly that the only way these things could have possibly worked is to have diaphragms that are very, very heavily damped and to be running way off the resonance of the frequency. So you're in a very naturally flat region of these simple diaphragm structures. And in that limit of the very highly damped harmonic oscillator, it's the pressure that's driving it is proportional to the velocity of the stylus. So you get that same derivative frequency distribution as you do. So there's a lot there. And in fact, in one of the papers we wrote many years ago, we have a whole appendix going through all of this stuff about frequencies and response. So it's definitely an issue. Beata?
I realize that this is very important for historical records and collections that are vital to understanding past history. But a selfish point of view, I have dozens and dozens of 100-year-old 78s. So one sort of in the back of the mind wonders if there'll ever be sort of a commercial version of this, or some kind of processing place individuals could go with records, family records and things like that. Okay, so there is. I'm not sure it's affordable, but if you go to the Northeast Document Conservation Center, they do projects for individual customers, people. And they just got covered. They sent me an email earlier today. A man came with his grandfather's voice from World War II, and he had never known his grandfather, on this cracked thing from Armed Forces recording, and they played it for him, and it was a very meaningful thing, for his family, and it had enough human interest that they actually did a radio story about it. So you can do things like that. For your large collection of 78s, if they're in reasonable condition, you can play them with 78 RPM stylus and things like that. So I wouldn't want you to invest your children's college education. The cracked ones, I don't know. If you're serious, yeah, if they're cracked, if you're a serious collector and you have, Robert Johnson or Charlie Patton or something really special, you could go to the Northeast Document Conservation Center. They're not there to gouge you. So they're very reasonable people. So nedcc.org.
Hi. Hello? Yeah. Can you tell me two things? One, can you tell me again what that linguistics person's idea was? Hearing the poetry of...
Oh, sure. Milman Perry.
And then I got to have a question about stereo.
Okay, so the question was, I'm not a classic scholar, so somebody correct me, but the question was, the Odyssey. Was there really a guy called Homer, and did he write this story himself? Or was it passed for many generations through an oral tradition and then finally written down at some point? Okay? And this was apparently not a well agreed upon idea at the back in the 30s and so forth. So Perry came out of studying with Kroeber, and so he certainly knew about sound recording and ethnography and so forth. Then he went to Harvard, and then he went to the Sorbonne. And in the Sorbonne, he was introduced to a scholar who had this idea that if you listen to present day, they called them singers of tales, people who were illiterate but could recite very long poetry from memory that they had learned through the generations, that you could perhaps study the form of that poetry and understand, how do they remember these long things? Are there structures in the repetitive phrasing, in the meter, in the relationship between words and phrases and so forth? You know, the wily Odysseus, the rosy-fingered dawn, you know, all this repetitive stuff that you found in the Odyssey, you find exactly those structures in this, in the Slavic materials that Perry collected, okay? So they then analyzed this, and his student Lord carried the work on. Perry, unfortunately, was killed by an accidental gunshot wound at the age of 29, just after coming back. But Lord continued this work through the 40s and 50s, and then the present Harvard senior classics people all studied with Lord. So there's a long tradition of this oral formulaic work, and the Millman-Perry collection of oral literature is a center at Harvard that has all the recordings.
And the other idea, how do you deal with stereo recordings that are modulated both horizontally and depthly? Okay. You have a way of doing all that.
So I didn't even mention stereo. So the recordings that are on discs that we talked about. So the groove moves from side to side. So that's only sufficient to encode one channel, mono, right? So how does stereo work? So the way stereo works is that they actually have the grooves moving, the sides walls of the grooves are moving at 45 and 45, okay? So that's a way of encoding two channels in a groove, okay? So in order to do stereo, we would have to either scan the groove in 3 dimensions, okay, or essentially what stereophonic grooves look like, if you look at them in this view, is the width of the groove is not constant. You see it modulates because the two sides are changing differently. So we could measure stereo with this technique, but stereo was introduced in 1958, which, by the way, was the same year that I was introduced. But you know, they mastered stereo on magnetic tape, and the quality of the stereo records on vinyl is pretty good. Most of the tapes are in vaults and archives. So there's very little real prerogative in this work to deal with the post-1958 world of stereo and vinyl. So there were ways to do it, but it's nothing we've ever really put any time into. Okay.
Okay, one last question.
Carl, you started with the premise that you had domain expertise in physics and you wanted to apply it to a different problem. I'm curious, over the course of the years in working on this problem, did you uncover techniques or learnings that you could go back and then apply in sort of your core domain?
Yeah, that's a great question, and the answer is absolutely yes. So it's funny that you should mention that, because particularly these large area scanning technologies, we just bought a 3D probe, an advanced version of the 3D probe that is in our Atlas lab that we're using for measuring the planarity and the vibrational modes of a very long and precise structure that's going to hold a whole array of sensors for the next generation of detectors that would go to CERN. The other thing is we build really large circuits, and we figured out, using this rotating technology. We wrap the circuits now around big cylinders and scan them optically to get huge high precision images of them, and so we can measure the location of all the markings and the fiducials and everything. So this technique, I mean, I've had students that they go back and forth sometimes between the audio project and the high energy physics. So yeah, there's a total circular flux of stuff that goes back and forth. So it's been really productive in that way as well. Okay?
This is a variation of your topic, but not quite what you're doing. Have you come across any procedures or methods or people that know how to handle old magnetic recordings, like wire recordings? I have a whole bunch of my mother playing piano on a wire recorder. Yeah. And some of these, sometimes they break because it winds up and pops.
So we have not worked on magnetic materials. I have been asked this question many, many times. And I think that there would be a bunch of sort of modern techniques that could be used to turn magnetic material into data. And as our colleague said, if you give me data, I'll turn it into an image. So I think there are ways, using X-ray polarization, which is sensitive to magnetization and stuff like that. But we have not done that. I mean, it's a whole other area that's low-hanging fruit that somebody could go for, but we haven't.
Okay, I don't see any more questions. So let's thank Carl again.
Thank you.